morning, everyone. Welcome to the second part of our talk, Biological Invasions in Southern Africa, a problem we can solve together. Please help me welcome our second speaker, Professor Julie Coetze. Professor Julie Coetze is someone who pioneers efforts to understand and combat the spread of invasive species, aquatic species, helping protect our water resources. Professor Julie Coetze, the stage is yours.
Well, thanks so much, Sela, and thanks to everyone for joining in here, and particularly to the students in your classroom. I hope that you will find some value in this. John gave a really great introduction to biological invasions, how they happen, why we need to worry about them, and to some extent what we can do about them. And as Sela said, I work on aquatic invasions. I work for the South African Institute for Aquatic Biodiversity, and I also work for the Center for Biological Control at Rhodes University. And the goal of what I do is to try and reduce the impact of these aquatic invasive species through biological control. Now, here are some maps of Africa showing Africa's worst floating aquatic macrophytes. And a macrophyte is just the term for an aquatic plant. And the four worst in Africa are, by far, the number one is water hyacinth, which you've had quite a bit of discussion around, giant salvinia or Salvinia molesta, which, as we'll see soon, is a big problem in the Okavango Delta, as well as other areas throughout Africa. Water lettuce or Pistia stratiotes, parrot feather, Myriophyllum aquaticum, and these dots come from the global from GBIF and from INAT, and it shows many dots across these continents, but these are largely historical records, and we should probably have some kind of facility where we can change the color of the dot to a site where we've got control, and largely the control of these aquatic species is biological control. And as John mentioned, water hyacinth is the world's worst aquatic weed, well, certainly the world's worst floating aquatic weed, and it really became a huge problem, or it was noticed in the 1990s when it invaded Lake Victoria in Kenya. Now you're looking at 200,000 hectares of a dam completely covered or almost completely covered by floating aquatic macrophyte. And here you can see a picture. This is at the Kisumu Yacht Club in Kenya. Sorry, Lake Victoria is not just Kenya, it's also Tanzania and Uganda. And this here is from Kisumu in Kenya. And you can see that that jetty looks as though it's going out into a field of grass, but it's actually all aquatic plant, all water hyacinth. Those boats can't get out. And so because of the importance of this lake to Africa, it's the largest freshwater lake in Africa. It was host, I say was unfortunately, to a high diversity of cichlid species, and of course important for fishing, for recreation, for transport, and essentially for human livelihoods. So when this plant covered, you can imagine the fear, the threats that this posed, not only socioeconomically, but also ecologically. And many different countries came in with all kinds of solutions. And as John said, this mechanical harvesting is not an ideal method for controlling water hyacinth, because as fast as these harvesters, which are largely developed in the global north, as fast as they're removing the plants are growing. So water hyacinth can double its biomass every 7 to 14 days under ideal conditions. And those conditions are lots of nutrients in the water and also warm weather. So here you can see there's a Natural Technology Limited aquatic weed harvester, and there's a little British flag on it. And this was awarded the Prince of Wales Award for Innovation in 1991. And if we went back to that yacht club in 1998, so 2 years after the deployment, not much has changed. That is still a sea of water hyacinth. So why do we get these species taking over huge wetlands, huge water bodies in introduced areas where in their natural range, and in this case, this is the Pantanal in Brazil, they co-occurring with the natural vegetation. And here you can see the beautiful Victoria reginae, the world's largest water lily, growing happily alongside water hyacinth. And in fact, the water hyacinth doesn't even look that happy over here. So what happens when these plants are taken from their place of origin and introduced into a new area? So we'll quickly have a look at a food pyramid or an energy pyramid in an aquatic ecosystem. And this is a generic. If you see the salmon, the salmonids, and the trout at the top, this is obviously again taken from a Northern European point of view. But essentially, we've got a triangle or a pyramid where at the bottom of the pyramid, we have got, oh, sorry, let me just go back here. At the bottom of the pyramid, we've got all the green stuff, the plants. The next level, we've got the herbivores. So those are the creatures that are eating the plants. Then we've got consumers that eat the herbivores. And then we've got secondary consumers that can pretty much eat herbivores and carnivores. And we can look at two different ways that energy flows in these systems. So we can look at bottom-up energy flow or regulation, or we can look at top-down. And if we first have a look at bottom-up, what's driving the amount or what's driving that ecosystem are limiting resources. And in this case, in an aquatic ecosystem, we'd be looking at the amount of water, which is generally not limiting. Nutrients, highly, highly important. And in this case, for aquatic plants, it's largely nitrogen and phosphorus. And then, of course, light, because without light, these plants can't photosynthesize, and therefore there wouldn't be any growth, or the energy from the sun is needed to turn the plants into more biomass. And so we've got this green circle that is limited. So the number of primary producers is limited by the resources in that system. That then determines how many herbivores are in the system, which then determines how many carnivores are in the system, which then determines how many secondary carnivores are in the system. And alongside that, we also have top-down drivers. And in this case, the two often work together. So we've got bottom-up resources that are allowing these plants to grow. And then we've got top-down regulation, where we've got carnivores eating the primary carnivores. The number of primary carnivores determine how many herbivores we've got. And that pressure of herbivory then determines how much green stuff we have. So how much of the plant biomass is being eaten. Now, when we come into invaded systems, they're often disturbed, and these aquatic plants are mostly the consequence or the result or a symptom of a disturbance. And in this case, the disturbance is largely pollution. And the pollution is in the form of sewage from wastewater treatment works, from agriculture, where nitrates and phosphates, so from animals' excreta, and from fertilizing crops runs off into water, and from industry. And so normally we'd have limiting resources in an ecosystem, but because of this input of nutrients, we suddenly have abundant resources, and so they no longer become limiting. And so that green circle of green stuff, of plants, becomes enormous. And the amount of top-down regulation that we have isn't enough to keep those resources, or isn't enough to keep that green stuff under control. And so we get these explosions of macrophytes, these plants, and also blue-green algal invasions. And this is just from a South African newspaper, News 24, where it shows that a tsunami of human waste inundates our rivers and dams. And that's because our wastewater treatment works in South Africa, our municipalities haven't maintained these. And so we are getting huge amounts of untreated wastewater just flowing into our aquatic ecosystems. And that is what is providing the amount of abundant resources, which then allows these plants to explode. So from a biological control point of view, or from a management of these invasive species point of view, what we want to do is increase the size of the herbivore pool so that we can increase the top-down pressure on those plants. And so the very context of biological control is that these plants arrive in their new area, they're free from their natural enemies, and in this case, natural enemies are these tiny little herbivores, mostly insects, that keep these plants in check. Often when you think of herbivores, you'll think of a hippopotamus or a manatee or a capybara, depending on where you are. In a terrestrial ecosystem, we all know elephants, giraffe, all the antelope. And so these plants arrive free from their natural enemies, and they get plonked into a system that is completely inundated with pollution, not always, but largely, and that allows them to proliferate. And so as biocontrol scientists, what we do is we go back to that point of origin, in this case for water hyacinth, or most of those floating aquatic plants that I showed you in the beginning, they all come from the Amazon basin, to look for those natural enemies, which we then introduce into the area of invasion as a biocontrol agent. And I know there's going to be lots of questions about, how do you know they're not going to eat another plant? How do we know that they're not going to become a bigger problem than the plant itself? Well, we do incredibly strict host specificity studies under quarantine conditions. And once we're satisfied with all of our testing, that can take from 3 to 10 years, we then apply to the relevant governments for permission to release these control agents. And this isn't just done in South Africa. It's done, in fact, Botswana's got biocontrol, Zimbabwe's got biocontrol, East Africa's got biocontrol, as well as Australia, New Zealand, the USA, Canada. And so it's a world-recognized management tool for controlling biological invasions. And the advantages of it is that it's environmentally friendly. So we're not applying herbicides to the system to control these plants. It's very low risk because there's never been an unanticipated host shift ever. So when people say, oh, biological control is not safe, they're not talking about weed biological control as we know it. It's self-sustaining and cost-effective because often these agents disperse themselves. So once the research is done and the agents are out there, the biocontrol will continue in the absence of humans, although I'll show you that we've actually had to change that. And it's permanent. These weeds can't escape their natural enemies. So they might fluctuate, their populations might fluctuate over time, but essentially, once that insect is out there, it's tied into the population ecology of that invasive species. And we've had fantastic success throughout Africa. Recently, we released a biocontrol agent from South Africa. We imported it to Kenya through colleagues with CABI. And this is a water lettuce invasion on the left in the Masai Mara. As we know, it's one of South Africa's iconic wildlife areas or conservation areas. And the little weevil Neohydronymus was released there. We released about 1,000 in May 2022. And by the end of 2022, water lettuce was under control. So what about water hyacinth? Why is it still the world's worst aquatic weed? Well, it's a very, very difficult plant to control. Now, if we go back to Kisumu in Kenya in 1998, scientists at the time from the US, from Australia, and from South Africa worked with the fishing units around the lake to introduce biocontrol agents to the lake. And they did this through mass rearing. So they got the communities involved because of the importance of clearing this weed to their livelihoods. And this picture actually is in Malawi. It's on the Shire River. And but we did the scientists did similar things in Lake Victoria, importing these swimming pools from South Africa and essentially farming the biocontrol agents, which these local fishermen could then release themselves onto the dam. So they took responsibility for their own for this environmental problem on their doorsteps. And very rapidly, we started to see control. And this is the weevils that were released, Neocatana bruchi and Neocatana acorniae. And it's really the little larvae that cause the most damage to the plants. They bury down the stem and they create waterlogging, and the plant eventually sinks. So if you have a look at that, the Yacht Club in 1998, the biocontrol agents were introduced in about 97, and by 1999, all but 20,000 hectares of that 200,000 hectares remained. And John showed the graph of that data. And can you even imagine the return of ecosystem services to the people relying on that system in that time? And what we've shown over time is that biological control can result in ecosystem recovery. So there's a whole lot of different studies here. Biocontrol of water lettuce facilitates macroinvertebrate biodiversity recovery. Water hyacinth reduces benthic macroinvertebrate diversity. Biocontrol of salvinia drives aquatic ecosystem recovery. And so over time, we've been able to show the benefits of biological control of these aquatic invasive species and the ecological benefits, and we've also been able to show the economic benefits. So if we compare the cost of chemical control to the cost of biological control, the benefit cost ratio is order of magnitude when looking at just biological control. So essentially what this graph means, or what this table shows, is that it's incredibly expensive to use chemicals to control aquatic weeds in comparison to using biological control. And not only is it the cost of the glyphosate or the chemicals, but it's also a reduction in the requirements of those costs. So you're no longer having to put that money into chemical control. That's so important. But water hyacinth remains a huge problem, particularly in South Africa, in Zimbabwe, where we've got these really nutrient-rich sites. And we've released 9 different species of biocontrol agents against water hyacinth in South Africa. And even though we've got all this feeding damage on the plants, you can see all kinds of damage there. And you imagine you saw this in your vegetable patch, you'd be freaking out because you're not going to get tomatoes. Your maize isn't going to grow. But with water hyacinth, with all that feeding, it still maintains itself. And that's because eutrophication limits the success of biological control. And that's largely because the plants can just keep taking up all those nutrients, even in the face of all that herbivory. And so, as we said, in the face of abundant resources, the amount of pressure that these herbivores can put on the primary producers is not enough. But we decided to release a biocontrol agent, another one, in 2013, this little hopper called Megamelus. And we decided to change our focus. Instead of just releasing a handful or a couple thousand of these insects, we decided to start mass rearing these insects and change our approach to an inundative approach, where we'd have a team of people rearing these insects, collecting these insects, and then sending them off to different sites frequently for control. And this is our Vionic mass rearing facility. It's called our Sisonke program, which means we work together. And this is a team of largely disabled people who come from our local community in Makanda in the Eastern Cape. They previously had no opportunity for employment. They were a burden on their families. And through this program, they now are employed by Rhodes University through our program. They get medical aid, they get a pension, and they are making a huge difference to environmental problems, not only in South Africa, but throughout Africa. And here you can see the guys collecting the insects with these little vacuum cleaners. We package them up into food containers and we can post them off. And we started this campaign, this inundative campaign, on a very large scale in 2019, where we started with these frequent inundative mass releases of the bug at a big dam in South Africa called Hartbeespoort Dam, which is just north of Pretoria. And in 2019, 35% of that system was covered in water hyacinth. It's South Africa's apparently our second biggest tourist hotspot. There's lots of people living around the dam, a lot of economy around that dam. And so the presence of this plant posed a huge problem. You can have a look at what the water looked like, nutrient rich, lots of sewage coming in from the rivers that lead into this from Johannesburg and from Pretoria. And these plants were just thriving. And we released Megamelis in 2019, and by January 2020, we were seeing an explosion of not only Megamelis, but also the Neocotina weevils. And this is because herbicidal spraying of the plants stopped in 2017. And in the absence of any chemicals on that system, obviously the plants exploded because they weren't being controlled by chemicals, but the insects exploded too. And so the weevils built up, but also the Megamelis built up through our inundative releases. And now you must think it's January 2020, the height of summer in South Africa, hot, lots of nutrients. That system that was 50% covered was now down to 5% cover purely through herbivory by the biocontrol agents. And we've done this now. We've been monitoring this system. We've been doing inundative releases every single year at the beginning of spring. And what we are seeing is so we've got 2017 to 2020, where there's various cover of water hyacinth in the absence of spraying. And at the beginning of 2020, that huge crash in water hyacinth. Over the winter, no water hyacinth at all. And then suddenly in October, November, we'd get an outbreak, or the plants would start to germinate again from seedlings. And so we'd have to re-inoculate those plants inundatively through our mass rearing efforts. And so we've seen this now every single year, and we're busy seeing it at the moment. Now in 2025, I haven't put that data in, these peaks and troughs because of herbivory by the biocontrol agents. So what we've shown is that by increasing that yellow circle of herbivores, by increasing that top-down pressure in the face of abundant resources, we can get control of even the world's worst aquatic weed. And we couldn't have done this without help from the community. We set up a number of these smaller rearing stations around the dam and showed that 6 years of community engagement with biocontrol implementation has resulted in the effective seasonal control of water hyacinth on Hartebeespoort Dam. And so, although waterweed biocontrol is limited by all these things, by eutrophication, I didn't talk about cold winters, but when it's cold, the insects die. When it floods, the plants wash out. We get interference from chemicals and these seed banks. If we adopt an inundative mass release program in the absence of herbicide operations, we can get control. But what's really, really important is stakeholder involvement. And really think about this in your own situations. How could you get involved in some kind of solution to an invasive species problem? And what we've done is taken this technology to the rest of the world. And I just quickly want to show you some of the collaborative work that's been done. Because we're talking with students in Botswana, I thought I'd just quickly talk about this campaign in the Okavango. There's a camp called Kanana Camp that obviously here's its position in the Delta. This is where we're talking about. And this section of the Delta has been invaded by a plant called Salvinia molesta, or Kariba weed. And through collaboration with the National Geographic Okavango Wilderness Project, we got involved with a biocontrol program, biocontrol solutions. Now, Salvinia molesta has been in the Okavango for a really, really long time. And the biocontrol agents were released in the 1980s, 1990s, and there's been various levels of control. And as this plant comes back and disappears and comes back due to hydrological changes, we see variations in the level of the infestation. And here's just another look. You can see how this plant is completely taking over that water surface and excluding those water lilies. And what the team from this National Geographic group did was they asked us how can they go about mass rearing this weevil for release in the Okavango. And this is the little weevil, Coetze salviniae. And this is the mass rearing that was set up in Maun. I mean, look how incredibly easy that is. A couple of wash tubs with the plant growing on it, and Coetze sent from South Africa to inoculate into these for release then into the Delta. And here's just a picture. You can see some very healthy green plants at the back where the biocontrol agents haven't been released yet, and here in the front. And so through this sort of farming of these insects and releasing them, here you can see one of the guys on his makoro, I hope that's what it's called in Botswana as well, with these tubs of salvinia that are teeming with the biocontrol agents and releasing them for a nature-based solution. Here's another picture of a tub of these plants, and a couple months later, coming back to these systems and the results of biological control. I think I've probably run out of time. So I do have a lovely story from Cameroon. It's very similar. I'm going to just skip right to the end. So this is this system called Lake Ossa. It's the biggest breeding habitat for the African manatee. And in 2018, 2019, it was completely taken over by Salvinia molesta, which they called Boko Haram. And you can imagine the devastating economic, ecological, social impacts. Here, people are trying to physically remove it. And the more that the faster you're removing it, the faster it grows. So the same thing, the little Salvinia weevil was introduced. And in 2021, we could see that 50% of the system was covered in Salvinia. And the manatee disappeared. There was no sign of the manatee. The insects were released through a collaboration with us at the Center for Biological Control and Louisiana State University, as well as the African Marine Mammal Conservation Organization, which was based in Cameroon. And 2 years later, down to 17% cover. And most of that cover was a grass, an indigenous grass growing on top of the Salvinia. Don't worry about this, just to show that the green was Salvinia, which we could tell from satellite imagery. And by the middle of 2023, there was no Salvinia left. And the most exciting thing about this was the appearance of this creature. And if anyone can tell me what they think that is, you can get a beer. So thank you very much. If there's any questions, if anyone wants to guess what that creature is.
Thank you so much, Professor Julie Coetzee.